Hello, welcome to this course, Systemverilog Object-Oriented Programming, an example of converting a module-based test bench to a class-based test bench. This is a short course showing only an example, and in the example, first you will be writing a simple Systemverilog test bench based on modules, and then you will be converting that into a class-based test bench. So if you're somebody new to Systemverilog, you can watch the playlist that I have given in the I button, which is an introduction of Systemverilog and which will help you to start learning Systemverilog. And also you can watch the two basic level TestBench coding courses in Systemverilog, which is again you can find in the I button and links in the description below. So before we start on, please do subscribe us if you haven't, and also visit our website at systemverilogacademy.com. Now let's straight away go into the problem. Before starting off with the example, this is what we are going to model. We have a DUT and a test bench, and we are going to write Systemverilog code for this test bench. The DUT have a simple AXI interface, and to make it very simple, we are just assuming that it has only one AXI interface, which is the write address interface. If you are not familiar with the AXI protocol, don't worry about it. Just understand that it's a protocol based on valid and ready. It has got 5 channels, and we are only worried about one channel, which is the write address channel here. And also, to make this example simple, we are only worried about few signals in this write address channel, which are the ID, address and length field, which are of length 3 down to 0, 31 down to 0 and 3 down to 0. And also it has got a valid and ready signals, and note that the name of all these signals are starting with a prefix of AW. And also every channel has got a clock and reset signal in that. Now to start writing the test bench, you need to write the DUT code as well, because if without the DUT you won't be able to write a test bench in Systemverilog. But if your intention is to just learn Systemverilog test bench coding, there's a simple technique for that. You can just write a dummy DUT or dummy DUT and straight away jump into writing test bench code. In the dummy DUT, you just write the minimal code, which even need not be synthesizable. You can even write test bench constructs in the dummy DUT and start coding your test bench directly. So this is a very good technique to start learn Systemverilog test bench coding, irrespective of what kind of TB you wanted to write, like whether it is a simple module based test bench, or whether it is a class based test bench, or even whether it is a UVM based test bench. This will be our approach in this case. So first we will be writing a simple Systemverilog interface to write this AXI write address channel. Then we will be writing a simple dummy DUT or dummy DUT, and then we will be writing the test bench code for this dummy DUT, which is module based or the old Verilog style test bench. And finally we will be converting that test bench into a Systemverilog class based test bench. So we will be starting with the interface and DUT. So I'll be using the EDA Playground platform to write code and simulate it. And if you're not sure how to do that, watch the video in the I button, which will describe you how to use this platform. In the design.sv file, we will be writing the interface and the dummy DUT, and in the testbench.sv file, we will be writing the test bench code. So we are defining a Systemverilog interface by using the interface keyword and the end interface keyword. The name of the interface is AXI write ADDR interface. It has got the input of clock and reset, and these are the signals in that, which are ID, address, length, valid and ready, and those are the ones which are described in the AXI write address channel description. Again, if you are not familiar with Systemverilog interfaces, you can watch the video in the description, which will teach you the theory of interface and Systemverilog mode ports. But for now, in simple words, a mode port in Systemverilog interface is something that can be used to define the direction of signals in the interface, so that the same interface can be used in multiple module instances, like in the master and in the slave. There are two mode ports here, a master and a slave. An AXI protocol is a master-slave protocol. And when it is acting as the master, the signals ID, address, length and valid will be driven by the masters and they will be output, and ready will be driven by the slave and it will be input, and when it is slave, the vice versa. So next is our dummy DUT. So I'm just giving it as a name like sample DUT. It has got input which are clock and reset, and the Systemverilog interface which we have defined here, which is AXI write address interface. And when you use interface within the port list of the Systemverilog module, there itself we can define the direction of the signals by using the appropriate mode ports. So here the DUT will be a slave, therefore we will be making this interface as slave in the dummy DUT by declaring like the interface name dot the mode port name, and this is the port name. Now the code in the dummy DUT is very simple. It just need to drive the ready signal. So I'm just using a urandom function. It will give appropriate random values to the left hand side variable or signal to which it is assigned, limited by the width of the variable or the signal. Here in an always block, I'm just assigning this interface dot ready will be equal to urandom. Next we will be writing the TestBench code. The TestBench is writing the testbench.sv file, and here is a TB code. I'm using a module named TestBench with no argument. So my intention is to drive some random values to the interface or some random values to the signals. Since the DUT is a dummy DUT, I'm not doing any kind of checks here. I'm just doing the driving part so that we will be able to see some signals in the interface. For that, these are my internal signals. I need to use a clock and reset signal to drive the clock and reset. And I'm using an internal variable named number of transactions is equal to 10 so that I can send 10 transactions in a loop. And next is the instantiation of the DUT and the interface. You can see that the sample DUT is instantiated with the name sample DUT1. Into that, the clock and reset signal will be passed by using the dot star, as we are using the same names for the internal variables. And this AXI write ADDR INDF1 will be passed as m underscore interface, which is nothing but an instance of the same interface here. So what all you need to do in the TestBench is to drive signals into this m underscore INDF instance of this AXI write address interface definition. And this is how you use a Systemverilog interface in the module port list. And next, these slides are for seeing the waveforms. And here is a clock and reset generation. And after that, I'm writing the TestBench functional code here in an initial begin. As our intention is to convert this TestBench into class-based TestBench, instead of writing everything within the initial begin, straight away I'm structuring this TestBench in a nice manner so that it will be easy to compare this one with the actual class-based TestBench. So I'll be writing tasks here instead of directly writing all the code here in the initial begin. And even if you're writing a simple Systemverilog module based TestBench, it is always a good practice to use tasks or functions to separate some functionality so that it will be easy to reuse and even understand by a third person. Before the reset, you need to initialize the signals. At least you need to initialize the valid signal. So I'll be using a task called init signal, and then I'm waiting for the reset, and then in a for loop, I'm driving 10 transactions into the DUT by using another task called drive write ADDR. And finally, after waiting for a clock, I'm calling the $finish function to end the simulation. And if you're not adding this clock wait here, you won't be able to see the last transaction in the simulation. Now let's see the tasks here, which are init signal and drive ADDR. So first is init signal. So this is the init signal task. Here I'm just driving the valid to a 0. And when the valid is 0, as per the protocol, other signals are down case. If you want, you can drive 0 to other signals as well. And the last part of this TestBench is this drive ADDR task. So within the task, before driving some value to the interface, just wait for the ready signal in the interface. So we'll be waiting in a loop until the ready is asserted by the slave. When the slave is ready, drive all the signals with some random values. As we said earlier, the $urandom function will return a random value which will be limited by the width of the signal to which it is assigned. So here ID, length, address will be assigned with some random values, and valid will be asserted as 1. Next, we'll wait for a clock cycle and make valid as 0. And finally add a nice log message into the log files by using the $display function. I'm just printing like drive ADDR at time I'm sending this transaction with these values. You can see that the first argument is $time and next are the values which we have driven already. This is a non-blocking assignment in Systemverilog, and if you are not familiar with this, you can again watch the video in the I button, or the same link is given in the description as well. So here we have written a simple Systemverilog test bench, and next let's run and see the result. Save, run. So the waveform window has opened up, and let's see some waveforms. Get signal in the interface. Let's add all. You can see that after the reset is deasserted, the ID, address, length are driven with some random values. And also you can note that whenever the ready is low, it will wait until the ready is high, and then only the next set of values are driven. So here it is waiting for 1 clock cycle for the ready, and here is again 3 clock cycle for the ready. So just to show you all the transaction, I am just zooming out. You can see that all 10 transactions are driven into the interface. And also have the look at the log file here. It is printing whatever we have added in the $display. There are 10 display messages here, you can see. Let me just zoom in here. At 6,000, sending a try transaction with these values, and at 7,000, and again at 9,000, at time 11,000, and so on. So that is the end of this session. Here you have seen how to write a simple Systemverilog interface with a set of mod ports in that, and also you were told about the concept of using a dummy DUT, which will help you to start writing TestBench code immediately. And also you have seen a simple Systemverilog module based TestBench. And next you will be converting the same TestBench into a class based TestBench. Now let's convert the same TestBench into a class based TestBench. For that, instead of writing everything into a class-based test bench, again here let's take a step-by-step approach. First we will be only writing a simple transaction class and use the same Systemverilog module-based test bench to drive transaction into the DUT. And then in the next example, we will be converting the whole test bench into a class-based test bench. So let's go through the bare minimal theory part which is needed to start learning class-based test bench. In a class-based test bench, first you need to model transactions as a class. A transaction is an entity that is going into an interface. To drive these transactions into the DUT, again you need to write another set of classes which are generally called as a driver class. In this example, we will be writing the transaction class. For that, the design part of your code will be the same as that of the previous case, and in the test bench part there will be some modification, and we will come to that. And before that, here I am adding another file named axitxn.svh, and also I am including that file in the beginning of the file so that this code will be available here. And first let's take a look at the axi transaction class file. So within the axitxn.svh file, I am writing an axi transaction class. So you will write the Systemverilog classes in a class and n class keyword, and this is the name of your class here, which is axi_txn. This class has got 3 data members in it, which are ID, length and address with appropriate width that is defined in the actual axi protocol. ID and length are of width 4 and address is length of 32. And note that all these are defined not just as simple bit or logic, they are defined as a rand bit or a rand logic. So you can even use a logic here, it doesn't matter. So this is again Systemverilog specific random constructs. When you add a rand keyword to a data member, you can randomize the object of this class by using the .randomize function, which we will use in the test bench. Again, if you are not familiar with this and all, just make all the data members as random by using the rand keyword. This is a constructor function, the new function, and I have used this assignment of 0 just to avoid hangs in the function when it is used in the monitor class. But as we are not writing a monitor, you can just make it as an empty function here. The next is adding a constraint. This is again Systemverilog specific random concepts, and if you're not familiar, just understand that you can add constraint to a random variable by using the constraint keyword, and this is the name of the constraint. You can give it any name, and within a set of curly brackets, give the appropriate constraint you want to give, followed by a semicolon within the bracket. Here I'm making a constraint which is the length should be always greater than or equal to 1, because the length cannot be 0. And next, there are 2 functions in the class which are copy function and a convert to string function. For this example, you don't need to write this copy function. It will even work without the copy function, but this is a general practice, and I would say these are the two bare minimal functions which you might want to add to every transaction class. A copy function is required to do a deep copy instead of a shallow copy, and this will be generalized structure of every copy function. The transaction to which you wanted to copy will be passed to this copy function, and first you'll do a typecast and check whether you are getting the correct type of transaction, and if it is the correct type, copy each and every field of this casted transaction into this transaction by using this keyword. So you can skip this copy function. You don't need to write the copy function for this example, but I have added this here purposefully because this will be very much similar to a UVM transaction if in case in future if you are going to a UVM based test bench. And also there is another function called convert to string. So this is actual print function. The intention of this function is to call this function to get a nicely formatted string from this function with the current values of this transaction. Usually the transaction could have many data fields in that, and you might want to print this transaction multiple times in your test bench in different places. And to add debug messages, you wanted to print the actual value of this transaction in the log files, and instead of adding the code to explicitly print the individual data member value, just call a function there so that it will return a nicely formatted string with the current values. Here I'm using a local string named RPT, and using a $s format, I'm passing a nicely formatted string to this RPT and returning this string here. This will be more clear when we actually use this function in the code. Now, if you want to make this example very simple, you can even delete this copy function. So this will be the bare minimal class which we need to simulate this example. Next, let's see how do we use this transaction in the TestBench code. In the testbench.sv file, don't forget to include this file, and all these parts are exactly same of that of the previous example. And in the functional part, we will be initializing the signals and waiting for a reset, then drive 10 transaction in a loop. This time there's a change in the drive ADDR function. We are passing a transaction argument into this task, and whatever is the value getting as the argument here, that transaction.id, length and address are driven into the interface within this drive write ADDR task instead of the urandom here. For that, you need to use an object of this transaction locally here within the initial block. So we are defining an object of the axi_txn class with a name txn. In the for loop, before passing this transaction into the task, you need to create the object by using the new function, and also you need to randomize by using .randomize function. So for first you need to create the object by using txn equal to new, then write like txn.randomize. When an object.randomize is called, all the random data members of this object will get random values, and therefore when this line is executed, the transaction object will have random values for its ID, length and address field, and we are passing that transaction into the drive write ADDR task, and therefore these values will be random here. So this function is exactly same except that we are using the transaction values instead of urandom values. Now let's run and see the result. You can see that the same set of results are appearing here. And also have a look at the display messages. Drive write ADDR at time 0 we are sending the transaction. But there is a slight change in the code here. In the display message, instead of listing down the individual transaction values, we were just using the transaction.convert to string function. When this txn.convert to string function is called, it will return a nicely formatted string messages with the current value of this transaction, as you can see here. And just by using that function, you will be able to add display messages. In this example, we were using only one display. So you might think it doesn't matter at all, but in an actual complex test bench, you might want to print the values of the transaction multiple times, and then it will be convenient to use a function to return a readable formatted string with the current values of the data members of the class. As a summary, in this example, we have written a transaction class and we have used that transaction class to drive signals into the interface. For that, you need to create the object, and before driving, you need to call the .randomize function so that all the random data members will be driven with random values. And also we have used the convert to string function to display print messages into the log file. Next, we will be writing the actual Systemverilog class-based test bench by rewriting all these parts. In the previous session, you have seen how to write a transaction class, and as I said earlier, that was just an intermediate step, and we have to go on and convert the whole test bench into class-based test bench. This is a generalized block diagram of a Systemverilog class-based test bench. Mainly it will have a generator class, a driver class, and a transaction class, and the generator class will be generating transactions and sending it to a driver by using a mailbox, and the driver will be finally converting these transactions into the actual interface level signals and driving them into the actual DUT interface by using an interface. So it might look a lot of information, but if I'm saying in a simplified way, you need to write a generator class and a driver class and a transaction class as well. And finally, you need to use all these three set of classes to drive your DUT with valid input transactions. Now we will see the details. We have already written the transaction class in a separate file. Now I'm going to write the next class, which is an AXI generator and another driver in two separate files, and I have included these files into the main testbench.sv file so that everything will be compiled. Previously you are generating transaction from the module itself, but this time they need to be generated from a generator class. So here is the AXI generator class, and it has got a mailbox in it with the name mbox, and we will see where we are going to use it. And also it has got member variable with name number of write transactions. And in the new function or in the construction function, the mailbox has to be created again by using a new. This is mandatory, otherwise you will get compile errors. And next is another task named run. Generally you can give any name to this task, but typically it will be named something like a run task. When you call the run task of the generator, it needs to generate n number of transactions and send it into the mailbox. So here is the code, a local transaction object declaration, and within a for loop, this transaction will be created and it is randomized by using the .randomize function. If you don't know the assert statement, don't worry about it. You can even delete this assert and just call like transaction.randomize. And after randomizing the transaction, put the transaction into the mailbox by calling the put function of the mailbox like mbox.put of transaction, and finally add some display to the log file by using the $display and the transaction.convert to string function or whatever function you had declared for print. Previously, after randomizing the transaction, we were directly driving it into the DUT within the TestBench module itself, but when it is writing in a generator class, you won't send it directly from the generator, but you will add the transaction into the mailbox, which is again a member of this generator class. Next is a driver class. In the driver class, again it has got another mailbox and the same variable number of write transactions, and also additionally it has got an interface which is same as that of the interface that we have declared here, AXI write ADDR interface with the name of m_indf, and note that it has to be a virtual interface. So you should always add the virtual keyword here. And again, don't worry about what is virtual here if you don't know the virtual concept of object-oriented programming. But while you declare the interface, it has to be a virtual interface. And in the new function, create the mailbox by using another new and add another task, say run, which will take the transaction from the mailbox and drive it into the interface. So within the run task, there is a local transaction declaration. And before driving anything, it needs to be made sure that this interface is assigned correctly or tied up correctly to the final DUT interface, and check whether it is null or not. If it is null, flag an error so that you can avoid unwanted debugs. And after that, you can see that this part of the code is pretty much same as that of the code that you are writing in a module-based test bench. So this was your first module-based test bench. In the initial begin, you can see that you are initializing signal and waiting for the reset and driving this. And this was your drive ADDR transaction. So we just moved this part of the code from the module-based test bench to the driver class here. But the slight difference is before driving the transaction, first you need to get the transaction from the mailbox in the driver and then drive the transaction. Now this task is exactly same as that of the previous case where you were modeling the transaction and writing everything in the module, and this is the general anatomy of a Systemverilog driver class. Within the generator class, we were generating n number of transactions and putting it into a mailbox, which is again a member of this generator. Within the driver class, there was another mailbox as a member, and we were taking the transaction from the mailbox and driving those transactions into the virtual interface, which is another member of the driver class. Now what we need to do is you need to instantiate the generator and the driver class within your top level test bench module. And also you need to connect them together by using the mailbox, because there's a mailbox instance within the generator and the driver, but you need to make sure that they are connected together by using an external mailbox. And finally, you need to connect the driver virtual interface to the actual DUT interface as well. Now let's look into the code. Now here is the testbench.sv file, and note that even though you are using the class-based test bench, there has to be a top level module, a test bench module, where you will instantiate all the classes. All the functional part will be moved into class, but there has to be always a top level test bench which will instantiate all the classes and the DUT and the interfaces and do the appropriate connections. Now within the module, the AXI write address interface is instantiated and it is passed to the DUT instantiation as well. And additionally, you can see that the driver and generator class objects were also declared here with the name m_driver and m_gen. And these parts were exactly same as that of the previous case. And now let's see the functional code. In the functional part, you can see that I am using a local mailbox here with the name mbox1, also calling its constructor the new. And next I am calling the constructor of the driver and the generator class, because you have to always call the do function of the object before start using them, otherwise you will get null object error. The next part is connecting them together. There was a mailbox in the driver and in the generator, and also there is a mailbox locally here. If you just assign this mailbox to those two mailboxes in the classes, then both classes will be using the same mailbox, and this connection can be made very simple. So here mdriver.mbox is equal to mbox1, the local one here, and mgen.mbox is equal to same mbox1 here. Now the mailboxes are connected. And also don't forget to connect the driver virtual interface to the actual interface. Therefore, the mdriver.m interface, which was the virtual interface in the driver, is equal to the local instance of the interface, which is m_indf again. With these two lines, we connected the driver and generator, and in the next line, we connected the actual DUT interface into the driver virtual interface. And also note that this m_indf is also passed to the DUT module instantiation. Therefore, when the driver is driving signals into the interface, it will be driven into the DUT. So all the connections are made. Now the final part is doing the actual functionality. Both in the generator and in the driver class, the functionalities were written in a separate task. We named the task as run. Therefore, to start the functionalities, you have to call the run task in those two classes in the main module. That is done in a fork join. A fork join will wait until all the launch tasks have been finished off, and also these two will be started off parallelly. The driver will be always waiting to see a transaction in the mailbox, and when the generator actually sends something into the mailbox in the generator.run task, the driver will get the transaction in its mailbox. Because we made a connection by using a local mailbox between driver and generator, and thus generator will be generating and driver will be getting those transactions or taking those transactions and driving them into the DUT. So when the generator and the driver have finished off, it will unblock the fork join and execution will continue from the next line. Here, after waiting for a clock cycle, just call the $finish and the simulation will be ended. Now let's run and see this. Let me just zoom out a bit to see everything. You can see that 10 transactions has been sent out, and also look at the log file messages that we have ordered in the driver and generator class. You can see that the AXI generator is generating everything within 0 time or before starting anything off and putting it into the mailbox, but there is a delay in the driver execution because within the driver there is an actual wait and clock synchronization. So the driver code will be advanced along with only the clock signal, but within the generator code there was no delay factor. So all these execution have been finished off in 0 time. And that's the reason you are seeing all the 10 messages within the generator first and followed by the messages in the driver. Finally, you have reached the end of this course, and here you have seen how to write a simple Systemverilog class-based test bench. You have initially written a dummy DUT and a simple Systemverilog interface and a module-based test bench, and then you converted it into class-based test bench step by step by first modeling transactions in a transaction class, and finally using a generator and driver class to complete the whole Systemverilog class-based test bench. This is a generalized approach, and this will be true even if you use UVM or OVM to write test bench. Or in other words, you might see a lot of similarities even if you convert this test bench into a UVM based test bench. I have added the links to YouTube videos which is teaching the different Systemverilog concepts that we have discussed here, like Systemverilog interfaces, mod pods, mailboxes, fork join, etc. And take a look at them if you wanted to learn more about any of them. So that's the end of this course. So before winding up, please do subscribe us in YouTube if you haven't, and also take a look at our website at systemverilogacademy.com to find more Systemverilog courses and training programs. Thank you for watching. Happy learning.